All right, let's get right into this. We're going to break down a really important paper today. It's called The Mosaic Memory of Large Language Models from Nature Communications. And believe me, this one fundamentally challenges a lot of what we thought we knew about how LLMs remember things.
We're just going to start right here with this quote from the abstract, because it just lays it all out. The standard wisdom, the thing we've all been working with when it comes to LLM memorization, it might just be wrong. This isn't some small incremental finding. It's a sign that we might have been looking at this whole problem completely backwards.
Okay, so to really get why this paper is such a big deal, we have to first talk about the central myth that it completely dismantles.
So, for the longest time, this has been the bedrock assumption in the field. The idea is really simple, right? If a specific chunk of text, a line of code, a name and address, shows up over and over and over again exactly the same in the training data, well, yeah, the model's probably going to memorize it. But if it doesn't repeat exactly, we've mostly considered it safe.
And look, this isn't just some abstract academic debate. Our most critical real-world safety protocols are built on this idea. Things like scrubbing personal info for privacy, removing copyrighted text, even decontaminating our benchmarks to make sure tests are fair. It all assumes that you just have to find the exact matches. This myth is actively shaping how we build and how we trust these massive models.
So if that old model is broken, what are we supposed to replace it with? Well, this is where the researchers introduce a brand new framework they call Mosaic memory. And here is the absolute key. A model doesn't need to see the exact same sentence 100 times to memorize it. Nope. Instead, it can see 100 slightly different, overlapping versions of that sentence and literally stitch them together, piece by piece like a mosaic, to form a super strong memory of the original.
Now, to actually measure this, the authors came up with a really brilliant metric, rho, or rho. They call it the exact duplicate equivalent. Just think of it like a power rating. If a slightly off, fuzzy duplicate has a rho value of 0.5, it means seeing it once is half as powerful for memorization as seeing one perfect verbatim copy. This is huge because it finally gives us a way to put a number on these fuzzier kinds of memorization.
So how in the world did they test this? They designed this super clever canary experiment. First, they create these totally unique text sequences, the canaries in the coal mine. Then they inject the original canary and a bunch of its modified fuzzy cousins into the training data. And finally, they use membership inference attacks, MIAs, to see just how well the model memorized the original canary. It's a direct test. Does seeing the fuzzy versions make the model remember the original more strongly?
And here you go. This chart is basically the smoking gun. What it's showing is pretty clear. Even as the fuzzy duplicates get more and more different from the original, that's the Levenshtein distance increasing on the x-axis, their power to cause memorization, that rho value on the y-axis, stays way, way above zero. It's a perfect illustration that even text that's been changed a lot still contributes to memorization.
Now, let's put a hard number on this, because this is where it gets kind of nuts. The paper found that a fuzzy duplicate with just 10% of its tokens replaced has a rho value of 0.65. What does that mean? It means it contributes 65% as much to memorization as a perfect word-for-word copy. Think about that. Seeing just two of these slightly altered versions is actually more powerful for memorization than seeing one perfect copy. That is a staggering finding.
Okay, but this is where the story takes a really weird, unexpected turn. You'd think, right, that this whole memory stitching thing has to be based on meaning, on the model actually understanding the semantics of the text. But that is not what they found.
Here's the twist. This whole powerful mechanism, it appears to be syntactic, not semantic. It's all about the raw statistical overlap of tokens. It's not about the model having some deep, abstract understanding of the information.
I mean, the comparison just makes it crystal clear. When they tested versions with high token overlap, just a lot of the same words, boom, they saw strong memorization. But when they used paraphrased sentences that kept the exact same meaning but used different words, the memorization effect was incredibly weak. For models that we celebrate for their semantic reasoning, that is a truly wild and counterintuitive result.
Okay, so this is a fascinating academic finding, no doubt. But so what? What are the real-world consequences? This is where it gets absolutely critical for anyone actually building or deploying these models.
Yeah, this isn't some phenomenon that only happens in a lab.
The researchers took a look at the slim pajama dataset, which is already supposed to be deduplicated, right? It's supposed to be clean. And what did they find? For a sequence that had 1,000 exact copies, they found, on average, 3,000 times more fuzzy duplicates nearby. At a greater distance, they found over 20,000. These near duplicates are absolutely everywhere, and our current tools are completely blind to them.
So the implications are just profound. Our privacy filters? They're basically sieves. Copyrighted material can get memorized even if the exact text was never in the training data. Our benchmark scores are probably inflated because models have seen fuzzy versions of the test questions. And machine unlearning, trying to make a model forget one data point, is like removing a single tile from a mosaic. The picture is still there.
And that's where we have to end it. With the central challenge this paper throws at our feet, it shows pretty convincingly that our main defense against this stuff, simple exact match filtering, is fundamentally inadequate. It's a broken shield. So the critical question for all of us in this research community is, what does the new shield even look like?